4.2 Soil formation and erosion. Physical weathering. This is where you're taking rocks and you're breaking them down mechanically into smaller pieces of the same rock. You're not changing what it is. Chemically, it's identical. You're just turning it into little pieces. This takes a very long time. Rocks are patient. It can be caused by both biotic and abiotic factors. Some of the abiotic ways: water can wear down rock, wind can wear down rock, temperature changes can result in this breaking down. Here's an example where you have water collecting in a rock. It freezes, which makes the water expand, and it makes those cracks just a little bit bigger. The next time it fills with water, those new cracks are filled as well. When those freeze, they expand and they also help crack. Eventually, you end up with smaller pieces. Biotically, plant roots can do the same kind of thing where you're having plant roots grow into these little cracks and they push. Plant roots are fairly strong. The main purpose of physical weathering is to reduce sediment size, which increases surface area, which makes chemical weathering more effective. In chemical weathering, you're breaking rocks down into their different mineral compositions. You're taking it and turning it into something else. You're breaking it down into its molecules. Now, that's important because there are a lot of nutrients that can be used in rocks that are not in a usable form. A very common example is phosphorus. There are many phosphates found in rocks, but they're not a usable form. So when those rocks are broken down, that phosphorus is able to be cycled through the ecosystems, through those biogeochemical cycles. Then we have anthropogenic chemical weathering. Here we have pollutants from the burning of fossil fuels. It gets in the atmosphere. It can mix with water and form acid deposition, aka acid rain, or it can drop in its solid form. That's called dry deposition. It's basically just dry acid rain, acid dust, if you will. The effects of acid rain: it increases the acidity, it decreases pH of soils, it affects waterways, which can affect plant growth. It impairs visibility, it makes it harder to see things. It can aggravate respiratory illnesses such as asthma and bronchitis, and it decays limestone. It starts dissolving some of these common building materials like concrete. This is a statue where the face is almost completely worn off. You can tell from the weathering that rain comes in frequently from this side. His nose is gone, and this part of his face isn't even recognizable as a face. Here we have trees and soil that have been affected by the acid rain. The pH has dipped below the tolerance range for these trees. These bushes are fine right now, but who knows for how long. How soil develops. From below, it develops as the parent material. The inorganic rocks are physically broken down, and it develops from above with the addition of organic material. You have these pioneer species move in. They start that process of depositing organic matter so the decomposers can start doing their job, and inevitably you end up with topsoil. Remember, that soil is a system of inorganic minerals and organic matter. Okay, we have mature soil and young soil. In mature soil, you have these very distinct soil horizons. If you were to look at a soil column, you can easily tell, okay, that's the O horizon, there's the A horizon, there's the E horizon, this one's B. Whereas in young soil, it hasn't had time to form those nice distinct layers yet. It's too young. It hasn't settled out yet. Now, mature soils can be rich in nutrients because they've had time to build up those nutrients. They've had hundreds of years for organic matter to cycle through. They've had years and years for the rocks to weather and add those nutrients. Or they can be very nutrient poor. If there's not a lot of disturbance in these soil systems, you end up with the same group of plants dominating, and certain plants use certain nutrients, so those nutrients in these soils end up used up. Or, because it's so old, water can have leached out most of those nutrients. Okay, soil horizons, they are in this order: O, A, E, B, C, R. And not all soil has the same soil horizons. Some have much more rich O horizons. Some have very small or non-existent O horizons. We'll look at those more right now. The O horizon. The O stands for organic. It's a layer of decomposing organic material. There's very little mineral in it, and it's called humus, not humus. These layers are very developed in forest ecosystems because you have all of that leaf litter falling off of trees, and it constantly replenishes this organic material. Where you have this decomposing material, you can have detritivores or decomposers. So this is very rich from a biological standpoint. The A horizon is also called topsoil. This is the layer of true soil that's closest to the surface. You have that organic matter from the O horizon that's mixed with the inorganic matter from the B horizon, from that parent material. This is where you have most of your biological activity. This is where most of your insects and other detritivores, where your plant roots systems are going to be, where your little burrowing mammals, earthworms, decomposers, this is where you're going to find most of them, here in the A horizon. The E horizon, this is the Eluviated Zone. It's usually much lighter than the other horizons. It's pretty distinct, and you can tell just by looking at a soil column which one is your eluviated horizon. And this is the level to which most nutrients are leached to. So this area is usually pretty rich in mineral nutrient. Okay, the B horizon is subsoil. This is where you start to have a lot more organic, inorganic mineral material and not as much organic material. You end up with a lot of slightly weathered rock. It's this parent material that has only slightly weathered. You have a lot of metals, not a lot of organic nutrient. Some plant root systems will extend this deep, but many do not. Then you have the C horizon. This is very similar to the unaltered parent material. It has barely weathered. I like to think of this one only counting as soil as the pity prize. It's, it tried a little bit, so let's count it. And then finally we have the R horizon. This is completely unweathered parent material. This is straight up all inorganic rock that has not begun the process of turning into soil yet. And here we have quick descriptors of the different horizons. We'll leave it there for a moment so you can pause and check them out. Okay. Soil profiles by biome. These are some specific biomes that you should know these properties of. Forests have very thick O horizons from that cycling of leaf litter. And they have very bleached E horizons. Grasslands have very thick A horizons. That's why grasslands are very good for growing plants. You have a lot of that A horizon, a lot of that topsoil, which has a nice blend of organic nutrient and inorganic chemical nutrient. You have a lot of biological activity. Rainforests have a very thin O horizon and almost no topsoil. Because the conditions are really great for growing plants, pretty much as soon as plant matter dies and releases their nutrients into the soil system, new plants will immediately grow and use up those nutrients. So there's no real time for decomposers to start to develop that O horizon. And because all of those organic nutrients are locked away in plants, you don't really have time to develop an A horizon. And then in deserts, because of low biomass, you generally have no O horizon. and you have very little A horizon for the same reason as in rainforests. There's not a lot of organic material available. Unlike rainforests, where it's because that organic material cycles back into new plants quickly, uh, in deserts, it's just because there's so little organic material to begin with. Okay, then we have slash and burn agriculture. This is where you can use the nutrients that are in plants in rainforest ecosystems and artificially create rich soil. The problem here is that when you chop down the plants and then burn them, yes, it does put the nutrients into the soil to be used, but a lot of this is used for agriculture, where you grow crops, then you harvest them, you chop them down, and then you transport them somewhere else for consumption. So you're taking the nutrients out of those biogeochemical cycles and you're moving them somewhere else. So very quickly, these slashed and burned fields become pretty useless for growing. Then you have to wait a very long time, hundreds of years, for nature to replenish the nutrients. Okay. Services provided by soil. Plant growth, that part's obvious. Cycling of nutrients, that part should be pretty obvious. Habitat, there's a lot of things that live in soil. It's not just macroscopic things that you can see, it's a lot of microscopic organisms. There's a lot of bacteria that live in soil. It's an engineering medium. You can build things on it or build things out of it. And it's an excellent tool for water storage and filtration. Things like wetlands, their soil is very porous. It's capable of holding massive amounts of water. So it's a great repository. You can use it for things like agriculture. A lot of animals use them as nesting grounds or breeding grounds. And soil is also pretty good at filtering out a lot of different pollutants.